video I want to talk about neuroscience. In particular, I want to focus on a paper by Professor Brian Butterworth, not a recent study, but a study that is specific and illustrates a particular point that I think is important to understand. I'll come back to the general implications later, but the design of the study, which is not Professor Butterworth's own work, he's reporting somebody else's work, but the study he's reporting is fairly typical of one kind of neurological study where the brain of an expert is compared with the brain of a novice. So in this particular case, in the paper called "What is a Prodigy?", the experimenters have put a German prodigy, a prodigious solver of maths problems, Rudiger Gamm. They've put him in a brain scanner. The technology as well is slightly old now, PET, but the same principles apply to fMRI scanning. And they've looked at what parts of the brain are being employed by Gamm when he does a complicated mental arithmetic. And they've then compared that with ordinary people, ordinary, not prodigious mental arithmeticians, and the comparison to see whether they use different parts of the brain. Well, obviously the first thing to do when looking at a paper like this is to have a look at the pictures. And figure 1 shows a top-down view of the brain showing the areas that are active in 6 non-expert calculators, as well as in Gamm. Those are the green areas, and the areas that were specifically active in Gamm, the areas in red. So the idea is here we're looking at a brain scan which shows that the green areas are used by Gamm and ordinary mortals when they do a complicated piece of a mental arithmetic, whereas the red areas are only used by Gamm. And the red areas are distinguished by being not areas that are specifically about mathematics. They're areas that are associated with long-term memory. The authors, that's the authors of the original study that Butterworth is reporting, the authors found that Gamm's calculation processes recruited a system of brain areas implicated in episodic memory, including the right medial frontal and parahippocampal gyri, whereas those of the control subjects did not. They suggest that experts develop a way of exploiting the unlimited storage capacity of long-term memory to maintain task-relevant information, such as the sequence of steps and intermediate results needed for complex calculation, whereas the rest of us rely on the very limited span of working memory. That's very important to see what an extraordinary claim that is. It says that experts, in this case an expert in mathematics, but we might also be thinking of an expert in music or in history or in some other specialized area, experts can use their brains differently from ordinary people. They can use parts of the brain that are normally used for storing long-term memory, and they can engage them in active processes such as mathematical calculations or remembering music and so on. So the claim being made here is that these experts use their brains in specialized ways that are not available to most of us. That looks like a claim that needs to be more closely examined. The example specifically that we're going to look at is taken from this paper, multiplying 68 by 76. Gamm has an enormous store of procedures and shortcuts that allow him to solve multiple step problems very quickly and accurately. For example, to solve 68 by 76 takes 7 steps and 6 intermediate results. After some practice with the task, GAM was taking about 5 seconds per problem with a high degree of accuracy. 2-digit squares, by contrast, took him just over a second because they were simply retrieved from memory. All of that detail is important in understanding what is going on when people do mental arithmetic calculations. And the conclusion is that, and I'll come back to the general conclusion later, that Rudiger Gam can use parts of his brain when he's doing a calculation that other people cannot access or cannot get to use for those functions. But let me go to one of the central arguments of the paper, which is, as Butterworth reports, if you multiply 68 by 76, then you need to make 7 different calculations, and keep in mind 6 intermediate results. Well, we know how we do this. 8 times 6 is 48. 7 8s are 56, plus 4 is 60. 6 6s are 36. 6 7s are 42. Plus 5, plus 3 is 45. As Butterworth says, we've got 1, 2, 3, 4 multiplications to do, additions, remembering the numbers that we're carrying over. It's a lot of work to multiply 68 by 76. And he states quite categorically, 7 calculations, 6 intermediate results to be remembered to get the answer. But is that really true? What would happen if we did the calculation rather differently? Suppose we said 70 lots of 76, 7 6s are 42, carry 4, 7 7s are 49, 53. Now we've got two lots too many of 76, so let's take away 2 lots of 76. That's 152. Take that away. We've got 8, we've got 6, we've got 1, 5. How would that do? That would give us the same answer, but going through a different process. Let's have one more thought about this. How about, for those of you who studied some arithmetic when you were in school, I suppose A is 72. And we know that 4 squared is 16. We've got to take 16 away from whatever it is. What's 72 squared? 72 squared is 5,184. Taking 16 away from that gives us 5,168. And in the paper, Professor Butterworth explicitly tells us that squares of two-digit numbers, Rudiger Gamm remembered those. He didn't need to think about what 72 times 72 was. He'd remembered that from his previous exercises in mathematics. So here we've got three different ways of doing the arithmetical sum, the mental arithmetic. There's the way you and I would do it. We would struggle to keep all of that in active memory while we were doing it. There's some shortcuts that might make it easier for us to do it. And then there's what a mathematician who'd spent a long time studying these mathematical problems might do, which is to use a formula or trick in order to shorten the amount of work. And we assume, and this is not just in neuroscience, but this is going to be important also when we think about artificial intelligence, that when we give someone a problem, they do it the way that we would do it. They're doing the thing that we would do if we were solving this problem, but they might be doing something very different. And that difference, the gap between the problem we set and the problem that people solve, is described by Adina Roskies as being the inferential gap. The inferential gap between this is the problem I've set and this is what I think the person is doing. And we assume, when we look at brain scans, that we're able to say, oh yeah, that person is using that part of the brain for this. There's an inference in there that is not exactly like looking at a photograph and saying, oh, that part of the brain does this and that part of the brain does the other thing. So let's now go back and see what the paper says in detail and try and work out what the general implications of this are for understanding neuroscience in education. Butterworth tells us that when making these calculations, such a sequence of operations of data and data handling would put considerable strain on normal working memory, yet many types of experts show increased capacities for the temporary storage of task-relevant materials. For example, musicians can recall tunes after a single hearing, and expert waiters can keep in mind the precise orders for up to 20 people without writing them down, at least until the customer is paid. Experts develop a kind of long-term working memory, which is a domain-specific episodic memory. Thus, despite their other talents, the musician and the waiter score normally on tests of digital span, for example. What Butterworth is telling us is that average people, normal people, non-experts, have a working memory that is limited, that can only store a certain amount of information in short-term memory, perhaps like remembering a telephone number between looking it up and dialing a telephone number. But that the expert is able to develop extra abilities, what he describes as long-term working memory. Or to put it in the words of Presenti and colleagues whose work Butterworth is reporting, the expert is able to recruit areas of the brain that are not available to the non-expert. So we've got an account here relayed by Butterworth about what the difference between an expert and a novice is. The novice has limited short-term memory. Whereas the expert has long-term working memory using areas of the brain linked to long-term memory. Now, long-term memory, all of us keep a lot of information stored in long-term memory. My telephone number, my address, my national insurance number, my date of birth, dates of birth of members of my family, all of that information is in long-term memory, and we can hold that in our minds or out of our minds for years without ever worrying about losing it. But we don't actually have to do mental operations on it. When we start doing mental operations, we're restricted to this limited short-term memory, except that the expert seems to be able to use parts of the brain that are not normally available to us. I want to offer you a different interpretation, bit of the difference between the novice and the expert. And that alternative interpretation is that the expert remembers things, task-related things. Rudiger Gamm has committed to memory the squares of all two-digit numbers up to 100. And he can recall those things from memory so that he reduces the amount of calculation that he has to do. The novice has not committed those things to memory and therefore cannot possibly recall them from memory and has to do the full calculation when it's set by the person who's doing the testing. So now, here's the alternative. The expert can use parts of the brain that normal people can't get to. That sounds quite a remarkable ability that they've got. They've shaped their brain to do different things, whereas the explanation that I'm offering to you says the expert remembers stuff. And that's less remarkable. That's absolutely unremarkable that in the thousands of hours that the expert has spent devoted to learning their specialist field, they've stored in memory a lot of things that are useful, shortcuts, tricks, cutting corners, useful pieces of information that they can just call up from memory and slot into their calculations, to their music playing, to their remembering the menus of the restaurant that they're working in. All of those things are stored in memory, and that looks much less remarkable. But it is an interpretation that also fits the data that we've got in terms of the brain scan. So I'm suggesting to you that we take with a pinch of salt the idea that that experts can do all these wonderful things with their brain. Maybe they just remember things. And that's a different way of looking at it. There is a problem here of going from setting a problem, setting a task, setting an activity for a person to do, like multiplying 72 by 68 or whatever the calculation was we asked the people to do, and working out what's going on in their head. And I'm arguing that neuroscientists don't have any particular special insight into that chain of reasoning from the task that they set to the calculations that people actually do to achieve them. When Gamm is doing those remarkable, apparently magical things with calculations, he's not doing the same thing as a novice is doing. So we're not comparing like with like. The expert doesn't need to do what the novice has to do in order to do the calculation. The expert pianist is doing something rather different from the novice pianist. And it's unsurprising, and it makes the neuroscience less remarkable that somebody who's an expert has previous experiences that inform their present experiences that the novice does not have. If you're new to educational research, you may think I've picked on Professor Butterworth's paper because I don't like it. It's true that I don't agree with his conclusions. I'm offering you a different interpretation of the facts than he is offering. And so we have a disagreement over how we should interpret exactly what's going on in this series of brain scans with an expert calculator and novices. But the fact that I disagree with the conclusion doesn't mean that I think it's a bad paper. On the contrary, I have chosen to use this paper because I think it's a very good paper. And think about the features that make it a good paper. Butterworth's paper is 2 pages long. It's a very short paper. But it had in it all of the information that we needed in order to understand the logic of his argument. Butterworth had provided us with all of the data that we needed to form our own opinion. He trusted us to be able to draw conclusions, to evaluate what he was saying and come to our own conclusions. That, to my mind, makes his paper a remarkably good paper. He could have just told us that Presenti and colleagues tell us that expert calculators can use different parts of their brain than other people when they're doing calculations. And that was the end of the story. He didn't do that. He presented us with all of the information we needed to weigh up, to think about what he was talking about, and to come to our own conclusions about what was working. So the fact that one disagrees with a paper is not the same thing as whether it's a good paper or a bad paper. You can disagree with a good paper, and that's a tip I want to offer you also in terms of choosing the papers that you refer to, choosing your citations. Because really, there are too many papers and too many books to spend time on ones that are not high quality. If you're going to use a reference, choose ones that you think are high quality. And it reflects your judgment. If you're using a citation and it's not good quality, that reflects badly on your judgment. So only pick the good papers that you to base your arguments upon. In that connection, I want to draw your attention to the opinion of J.L. Mackie, the philosopher, who, writing a book about ethics, in the preface said, "I am nowhere mainly concerned to refute any individual writer. I believe that all those to whom I have referred, even those with whom I disagree most strongly, have contributed significantly to our understanding of ethics." This is a book about ethics he's writing. Where I have quoted their actual words, it is because they have presented views or arguments more clearly or more forcefully than I could have put it myself. It's in that spirit that you should be selecting the works that you refer to, the literature that you use. Choose only the papers that are so forceful or so clear that they express things better than you could have expressed them yourself, even if they are opinions with which you disagree.